All right. Hey, everyone. So I'm going to jump right into it here. And I am on the main sort of page for this project, the GitHub README. And so I'm going to go and start with the object counting part 1 of this series. So if you scroll down to the Intro to Computer Vision section, and then you can just right click this and open this in a new tab. I already have this open, but go ahead and do that. Copy it so that you have your own version that you can follow along with. I think that's going to make this much more useful for people. So do that, and then we'll get started. So let's jump up here. So I've already gone through a few of these cells today, but let's see. We'll start at the beginning. So this is the Intro to Computer Vision with PyTorch Part 1, Object Counting with CNNs, right? So we're going to use a simple PyTorch model, a CNN feature extractor connected up to a fully connected layer. We're actually going to have 2 fully connected layers, but to determine the number of instances of different classes of objects. For us, these are just going to be shapes, simple shapes, in an image with this data set that we're going to build from scratch. And it's going to be some work, but I think it pays off in terms of what it gains us in terms of like really understanding the nuts and bolts of how these deep learning computer vision models work. And we're just keeping in mind that this is basically functioning as a building block towards getting us towards understanding Mask RCNN and faster RCNN, these sort of more like, state-of-the-art object detection models. So with that in mind, we'll start here with this relatively simple model of just trying to count the number of objects in an image. Okay, so we're going to go through all of these different parts of this Colab notebook, and each of the parts of this series have the same components. So we're first going to import, then we're going to build out this PyTorch data set that I'm discussing from scratch. Then we're going to basically compartmentalize that into a pytorch-lightning data module. If you're new to pytorch-lightning, I think this will be a great way to get familiar with some of the ways that works, and it's a super useful tool. Then we're going to go into visualizing that data, define a model, then go into overfitting a small batch. This is something that is easily skipped, but I think hugely important to do every time you build a new model. And then we're going to build this lightning module, which basically is this abstraction that torch-lightning has, where it basically contains everything: your loss function, your optimizer, your model, and like all the hyperparameters. And then you basically take that lightning module and a data module and you feed them to this trainer object, and it takes care of a ton of stuff for you and gets rid of a ton of boilerplate code. So it's really nice, and we'll go through all that. Then we're going to train, then we're going to visualize some predictions on our test set, and then that's it. So there's kind of a lot of like code that we're going to look at in a second. So I think I want to start with just visualizing what we are attempting to build first, and then going back through the code, getting in the details with some of these, annoying NumPy things, and hopefully that will make things make more sense than otherwise. Okay, so I'm going to click down here to visualize data first and go through some of the things here. So this is just, there's some utility functions here that I've built that most of them are like more or less based on some certain things in the PyTorch, some basic PyTorch tutorials. But all this does is displays a single image or list of images, PyTorch images, right? So if you're new to PyTorch images, one big thing to remember is that the color dimension comes first, right? So here I've got, whereas with NumPy and OpenCV, the color dimension is the second dimension if it's 0 indexed, right? So really the third. Okay, so yeah, here we're just visualizing some images. They don't have to be the same shape necessarily, and this is just some using torch.rand, which yeah, just is illustrating how that works. Then we have another function that adds some labels to the images. I'm not going to go into detail in this for the moment. I just want to get to this visualization of the data set itself. So let's look at this. All right. Actually, I'm going to pull myself over here a little bit. Okay, I'm going to be even smaller here. Okay, that looks good. So, okay, so this is a data set, the data set that we're going to build. These are 6 of the images. And so this might look like, what the hell is this? But if we look at the targets, so I'm going to click target labels to display the target labels. So the idea here is that we want to eventually train a model that counts these objects, right? So it counts that there's 1 rectangle, 2 lines, and 1 donut in this image. And that's going to be hard because these are super overlapping right here. But 2 lines, 4 donuts in this image, 2 rectangles, 1 line, 3 donuts in this image, and so on, right? So these are our targets. Those are the truth values, right, associated with these different images. And our goal is to build a model that can predict those just based on the image itself, right? An image that it's never seen, ideally, right? So, okay, so these widgets, IPython widgets, are really nice because you can start to sort of explore different functions and how they change with different parameters changing. So I really like this. So what we're going to do is look at what arguments the data set has and then start to mess around with things and get an idea of how this is working. So if we look up here, our data module object has some different parameters. So train val size, that's just the total size of the train and validation sets. Train val split, right? So there's going to be 6 images in the training set, 4 images in the validation set. This is just to visualize for now, right? And then the image size, the shapes per image. So we'll see what that, there's a high and a low. So we just distribute or sample from a uniform distribution between those two to decide how many shapes to put in each image. Then the relative class probabilities. So this makes it easy for us to easily create an imbalanced data set so that we can then see, like, okay, is our model robust against that? How is that affecting how our model is performing? Then we've got a random seed just so that this is deterministic, right? We can just create the same data set exactly given a seed. And then a class map. So this is basically what contains the information about the different classes, right? So we've got background and then a grayscale range. That's what this GS range stands for. And then the target color. So if you're not familiar with how colors work, you know, it's 3 8-bit numbers that represents a given color, right? So 255, 255, 255, that's going to be white. 000 is going to be black, and then it's RGB, so you can mix all the different weights and create different colors, right? So so our class 1 is the rectangle, and the target color is red. 2 is a line, target color is green, and then the donut is blue, right? So yeah, we'll see how that works. Those are just what we're going to use to visualize the targets and the targets. So in this one, because we're just counting, the color of the visualization is not really that important. But later when we go into UNET and object detection, you know, with especially Mask RCNN, this is what we're going to use to color our masks and very quickly be able to tell, like, okay, is the mask for this class making sense or not, or for this instance or whatever. Okay, and then we've got this object count. We've got this object count argument that basically determines whether or not the targets will just be actual counts of the different objects or just 0 or 1, like the image contains a circle or it doesn't. That's just going to be a binary, and you can, like, a model to predict on those targets could potentially be easier to create. So we have that option if we want to even do a simpler task than counting images, but we're not going to tackle that for now. We're just going to keep object count equals true. Okay, and then we start to get a, so this is the data module object that we have here that we're creating an instance of. And then you can see there's like this setup stage where it basically goes and like builds the two data sets, the training and validation data sets. And then you basically just iterate through the train data loader to look at some images and labels, right, by just calling that .next. So then we can make a list of images and feed those to our add labels utility function above, and all that does is it just tacks that label on that we were visualizing. Okay, and then we got our, we're gonna show this, the grid. All the grid does is just take 6 images or however many are in your batch and just put them all into one image for you to display. Okay, so now we can start messing around with some of these knobs and see what's going on here, get a little intuition. Okay, so image size, you know, I think that's probably pretty clear what that does. It's just going to make this like a little sharper, right? Because there's going to be more pixels in that image. And so obviously the nice thing about being able to tune the image size is that, like, when you're training on a data set of real images, those images are going to be big, right, if they're high definition images, and then you need a model that can deal with that, and you need to have you know, setup in terms of your GPU setup, or if you're running on clusters that can handle that. So that's why I started with this toy data set for myself, and I hope it's useful for others, because for some of these bigger models you can start with very lightweight like images and still get a sense for how all the targets work, and to make sure your model is, like, you know, making sense just before you go on to obviously the ultimate task that you're after. And for me, it's like I'm trying to build a model that detects physics signals in very large spectrograms. So yeah, I don't know how much people care about that, but okay, so let's make this image smaller again. And if you make it too small, it's going to be hard to read these words, right? Because those words are just built from pixels. So I won't make it too small. But okay, so then we've got class probability 1, right? So if I crank up class probability 1, what is that going to do? That's just going to increase the relative probability of rectangles occurring in our data set relative to the other 2 classes. And that is nice because then we can make imbalanced data sets, as I was saying. Okay, so I'm not going to mess with those. That's what the class probabilities do. They don't need to be normalized. it normalizes it for us, or we'll go through it. Then we've got the grayscale low and high. So remember, it might be a little confusing because these images are they are 3 by height by width images. They are not true grayscale images, because I thought that would make it much easier to like port all these models into real images. But they are grayscale in that each color layer is identical, which creates a grayscale image. So so you can basically change the grayscale range of any given class, the background. So 0 would change the background, right? So if I made it like 243 to 255 uniformly distributed noise, that's going to be almost white, right? And we see that here. Okay, so then we can also change the grayscale values for the rectangle for class 1 and 2 and 3, but I just didn't put them all here. So if I make this almost 0, then that rectangle is now going to look really dark. It's going to be almost exactly black, right? Whereas before it was sort of more, you know, fuzzy TV screen type thing. So then we've got the random seed, right? We just change that, and you're going to get a different set of images. Okay, so now I don't want to risk boring people, but I do want to go into some detail into how these data modules are actually built. There is decent documentation for them, so you should read through them if it's too fast. But let's go up and look at this. So because we kind of skipped. So first, yeah, we import things. I've put specific versions of all the main libraries that we're using, right? Torch, torchvision, pytorch-lightning, torchmetrics, matplotlib, numpy, opencv, and then this widget library to change around and look at our data set quickly, as we've seen. So yeah, so hopefully with those static version requirements, we can, like, hopefully this project will live on for a little while. Okay, it's saying I need to change to a standard runtime, but just ignore that. Okay, and then I will say, remember to, if you are not running this with GPU, you should do that. Well, maybe if you're just exploring for now, keep it CPU, but once we actually start training the model, we're gonna need it to be GPU. Okay, so let's look at what's going on here. So there are some of these base classes that are identical for each tutorial. So I'm going to spend this first one going through some of those. And these are basically just the classes that I've built to just draw these images or these shapes onto an image. And it's pretty straightforward. Yeah, you know, there are like SciPy methods that can accomplish similar things, or yeah, scikit image or something. But I did it by hand because I wanted to just do as much of this by hand and with as few libraries as possible. The YouTuber Aladdin person, I hope I'm saying his name right, but he has some awesome videos, and I really appreciate that he keeps the number of libraries super small. He just like does everything with just Torch or PyTorch, and I think that's awesome. I have expanded this to include torchmetrics, pytorch-lightning, because I think that without those, you get in the situation where you are building all this boilerplate code to like write your metrics to a data frame and track them manually and do all this stuff manually. And like, it's, you know, the future of deep learning is not doing all this stuff manually. It's going to become more and more automated. And as far as it seems to me, torch-lightning is how to do that best right now. But I could be wrong. Please comment in the comments if you have some other thoughts on that. Okay, so so this first class is just the draw class. This is just the thing that just you can call the draw.rectangle to draw a rectangle on an image, draw.line to draw a line on an image. I'm not going to go into this too much, but there's this RNG, that's the random number generator that NumPy has transitioned to, and you pass that around, and then you can have everything have deterministic behavior. It's really nice. Okay, so I'm not going to go into a ton of detail on that. Then there is the the computer vision DS, so dataset base. And so all of these data sets that we're going to build, we build one data set for this tutorial, one data set for the UNET tutorial, and then another data set for the faster RCNN and Mask RCNN tutorials. And you're probably thinking like, oh God, this has already taken so long and we're not getting towards faster RCNN, so maybe I should bail and just go watch that video. But I will say that like it's not going to be quick, but if you just go right to faster RCNN and you have no experience with that type of model, it might be not that valuable. You might be really confused. So this might be the slow way to do it, but you know, ultimately sometimes the slow way can be the fast way. Okay, so this base class basically just takes these different arguments: dataset size, image size, shapes per image, class probabilities, the seed, the class map, and it does just these sort of base things that all of these classes are going to do, like draw on images, build images and targets. It contains the get item method. So every data set that you build in PyTorch has to have a get item and a length method, and that is what makes it iterable. Basically, that's why you can do like iter data loader or whatever. So yeah, okay, so I'm not going to go into that, but now we're looking at the data set that is specific to this problem, the object counting data set, right? And so let's look at what is actually happening here. So so that super init, that's basically just initializing what this inherits from, which is that base class, right? And then we've got our images and targets that get built by this build images and targets method. And so basically each of the data sets that we're going to build throughout the tutorial series just have this build images and targets method, but they're just slightly different for each data set, right? Okay, so it's going to return, this method is going to return a data set. So this is a byte tensor, so that means 8-bit, right? So values between 0 and 255 of shape dataset size, 3 image size, right? Okay, that makes sense. And it says here that the images are grayscale. Each layer of the first color dimension is identical, right? So that's what I was talking about before. Okay, and then we have the targets. So this is going to be of shape data set size number of classes, right? Because for each image in the data set, we want to know how many of each class there are, right? So we'll look at an example of the data set in a second. But you know, for the first image, it's going to have, there's three rectangles, 2 lines, and 1 donut. So that's going to be 3, 2, 1. That's the you know, that's the shape, the number of classes, right? Okay, so yeah, basically this just iterates through the data set size. I'm sure this could be done in a fully vectorized way. I might try to put some effort into making that work, but it's really fast already. Like you can build 20,000 images in less than a second or something. So, but you know, I don't know if someone's interested in that. I could change the package so that that's that's what's, so that it's a little faster. But I will say all of these data sets and utility functions are built into this package, the PyTorch tutorials package that I have been building, which is, you could just copy and paste this code and you're there, but it basically is just so that you can get a little sandbox working as quickly as possible. And at the end of the video, I'll show you how to get that going, by just pip installing the package, and you're good to go. So, okay, so all it does is basically just builds these images, fills them with random shapes according to the arguments, and then builds these targets out, which just specify the number of each instance. Okay, so if that was super boring for you, just put me on ×2 speed. I will not be offended. But okay, let's look at the actual data set here. Whoa, for a second. So here I just built a 3-image data set. And we're going to look at what's going on here. So data set, so what I'm iterating through is just the dict of the object itself, right? So those are all the attributes of the object. And we've got data set size 3, image size 256, random seed. The class probabilities get normalized. The class IDs 1, 2, 3. The number of shapes per image 6, 2, 7. So the first image has 6, the second has 2, and the third has 7. And then the chosen IDs per shape. So, per image. So, this 6 images, they have this number, like first class 3, then class 3, 2, 1, and so on. So then we have our images, which are obviously kind of impossible to make sense of right now. But then we have our targets finally, right? This is what we care about. And that is 2, 2, 2 for the first. So let's make sense of that. So 2, 2, 2, if we go up here, there's 2 of class 3, 2 of class 2, and 2 of class 1. So that's where you get the 2, 2, 2. I said that in reverse order, but hopefully that makes sense. Okay. So I think that's enough about the data set. Let's go down. And okay, well, I will say here before we go on that the data module, if you're not familiar with these pytorch-lightning data modules, basically it's a way to group your training, validation, and test sets all into one object that then you can feed to this trainer object along with your lightning module. So we'll see how that all interacts later. But it makes it super nice, right? You don't have to keep track of all these different things. It's all built into the data module, and the way that I built this data module is like it does some of the splitting of the train and validation sets just automatically. So you specify a train val size, so you could say 100, and then the train val split is just a tuple of floats. If you'd put like whatever 0.9, 0.1, you're gonna have 90 training images and 10 validation images. And then you can specify your batch size, the test data set size, whether or not to shuffle in the data loader. So you probably do want to definitely shuffle your train and validation data, but maybe we won't shuffle the test data just so we can look at the same images easily once we start evaluating the model. Okay, so that's the data module. You can read through this in your own time. It's pretty simple. You basically just build a data loader for each train, validation, and test. And yeah, I don't know if you're new to Colab, it's nice. You can just click like, this data loader, and then it's gonna give you the docs right here. So that's pretty cool. Okay, so we already visualized the data, right? and saw what we're looking at. The one function I didn't go into is this add labels, which basically takes an image and then the targets and actually visualizes those targets as labels on the image. You can go through that if you want, but I'm not going to go into a ton of detail. OpenCV can be a little annoying just if you've never used it. Basically, it doesn't interact super nicely with PyTorch because you're going to have to be careful about taking things onto the CPU, converting them to NumPy because OpenCV wants everything in NumPy. Then you are going to want to switch the color dimension to the last dimension, and then so there's some annoying things. You can see the details here, but I thought it was worth it to be able to actually like visualize like these very easily. And then once we actually have predictions, we'll just click and be able to put the predictions down here to see how well our model is performing. Okay, so let's actually get into the model itself, which is right here. Okay, so the basic idea with a model that's capable of counting objects in an image is like you're going to have a bunch of conv layers, right, that are going to extract features from your image, and then you're going to have a fully connected layer that actually reduces all that like feature space into a prediction, right? So so what we're going to do is start with this double conv class, which we are going to reuse for the UNET tutorial in the next one, where we're going to do this same process but with UNET, with image segmentation. So, but basically, let's look at this double conv class. So it takes some in channels, it takes some out channels, kernel size, and bias, so whether or not to add bias, a bias to the conv layer. So what it does is, so if you're not familiar with this, sequential class is really nice. You can basically just put different layers together, and then it's going to automatically pass X through them, right, your image through them. And yeah, so it starts off with a conv layer, then it does a batch normalization, then it applies a ReLU, then another conv layer, and then another batch norm and a ReLU, right? And so this second conv layer actually doesn't change the size, like the number of features, but yeah, this is sort of taken from like the UNET implementation. So it's just a nice way to extract some features from an image. Okay, so now let's go into this object counter model. So this is actually where we build the model that's going to count these objects. Okay, so let's look at it. It takes an image size, in channels, number of classes, so that's going to be the output size, right? Features, and that's going to be a list of ints, right? And that's basically going to be like when you build these double conv layers, how many features do you want to extract in each one, and how many double conv layers do you want? Kernel size, so the kernel size is basically how big is that that filter that you're convolving with your image, right? The bigger it is, the larger the sort of like spatial information you're gathering from that convolution, right? And then this is that FC intermediate size. So we actually, once we do our feature extraction, we're going to have two fully connected layers, and that's the size of the intermediate layer there. Okay, And then bias, just whether or not you want bias in your conv layers. And then track X shape. So that's just like a utility thing that we'll look at for tracking the shape of our images as they get passed through the model, because sometimes that's one of the most confusing parts about getting used to these type of models. So, okay, so let's do it. Let's look at what's going on here. So first, we're just you know, building up all these attributes based on the arguments, and then we calculate the final size of the image. And so it's important how this works, right? So each step is going to reduce the size of the images by a factor of 2. So the length of that self.features, right? If you get the length of that, each layer is going to reduce by a factor of 2. So if image size divided by 2 to the length of the number of the features list, if that isn't an int, then it's not going to work, right? Because you're trying to divide like an image of shape 7 by 7 and you're trying to divide it by 2. So, you know, we could add some like padding and things to resolve some of that, but basically at some point you're not going to be able to reduce your image size anymore, and you're going to run into issues. So okay, so then we've got the yeah, so let's look at the actual the actual model and the forward class. So basically this is the feature extractor. So the feature extractor is just basically building up the double conv layer. So this is that double conv class that we saw above. It's taking some in channels, using the number of features as the out channels, and then swapping them, right? We'll see how that works in a second. Okay, so now we're looking at the forward method, which is what's interesting. And here we're just going to track the shape, and like this basically just takes X and then describes the shape of it at the current moment. And we'll see how that can be useful. So, oh, I'm getting tight. Okay, so for I module in self.feature extractor, X equals module of X, and then we're tracking the shape. So this is feature extractor layer I, right? And then we do a max pool with a kernel size of 2, and so that's going to reduce the image size by 2. That's actually what's doing the reducing of the image size, not the actual conv layers. And then we do those layers, right? So we're extracting features from the image. We reshape, right? So we lose the sort of, you know, image concept, and now we just have this list of features basically that we then use with some fully connected layers to make our predictions with, right? So we've got fully connected layer 1 into a ReLU, fully connected layer 2, and then we return X. Okay, so let's look at this and let's see how this works. So I hope you're following along here on your own, because I think that is going to help. So first we're going to just look at image size 256, batch size 13. I just like to make batch size something that's not divisible by 2 for these demonstrations, because when you have so many numbers that are divisible by 2, it gets wacky. Obviously a batch size of 13 would be kind of weird, but okay, so then, you know, we take 13.3 by 256, right? That's our input size, and we get out 13.4, 256, because the arguments that we fed double conv were 3 in and 4 out, right? So this is kind of our, like, you know, feature layer. That's the number of different filters that you're applying, right, to your image at that layer. Okay, now let's look at this. So this, we're gonna just do a little dummy illustration of the object counter model and get a sense for how it works. So we run that, and we're gonna just look at what this image, which had the input shape of batch size 13, 3 for color, 256 by 256, and then we're going to look at how its shape is changing as the image gets passed through the model. Okay, so feature extractor layer 0, 13, 7, 256. Okay, so that's because the first feature that we fed it was 7, right? We want to extract 7 features. Then the max pool layer reduces the image size by a factor of 2, right? Well, I should say the side dimension. That's really reducing the whole array by a factor of 4, but I'm often going to just use image size and just say the one side because I'm working with all square images here, so I hope that's not confusing. Okay, then we've got layer 1. Obviously we're 0 indexed here, and that's going to be now 11, right? Because 11 is the second one we had in our list. And then we're going to do another max pool, divides this by 2. Then we're going to have 15 for that, and then we do another max pool. And now we're down at just these 32 by 32 shaped objects, and we reshape, right? So this reshape, if you're new to reshaping, it's really nice, right? You just put in -1 and it deals with the rest. It's just going to make it the right shape, right? So x.shape of 0, so keep the first dimension, because I don't want to mix up my batch, right? You always want to keep the batch dimension intact because you don't want to be predicting like things between different images. You want it all to be on a per image basis. And then -1, that just basically flattens my image, right, into what? So if we look at the shapes here, 15 by 32 by 32, that's going to give you this 15,360. Okay, then the fully connected layer, right? The intermediate size was 10, and then a ReLU, that doesn't change the shape, and then another fully connected layer to give us this output dimension of 2, because I set the number of classes to 2 here. Okay, so yeah, here I just printed some stuff about the different conv layers. If you're new to how those work, I'm going to have a demonstration at the end of the tutorial of like visualizing how a conv layer evolves as the model evolves. So I think that'll be useful for people who are new to that. But yeah, read the docs on that. It's yeah. Okay. So next we are gonna go and overfit a small batch. I think this is a hugely important step to make sure that we know what is going on here. So this overfit function is going to take images, labels. I sometimes go back and forth between labels and targets. I mostly use targets, but I didn't here. So model, optimizer, device, and number of epochs. Okay, so what this is going to do is it's going to show us that we can overfit. What does that mean? It means that the model is capable of taking training data, overfitting on it such that it is perfectly predicting those, well, I shouldn't say predicting because it's the training data, but perfectly overfitting those targets, right? That's the first step to like proving that your model could at least potentially work, right? If it can't do that, it's never going to predict on images it's never seen before. Okay, so let's go through this. I would just like watch some of the tutorials that I have listed at the top. I really should have gone over that in more detail. I have these links here. They're all pretty quick hits. Like if you click on them, well, except for like the PyTorch docs. Obviously, you're not going to read through all that. But these are mostly like quick YouTube videos. Again, this is the series by Aladdin Person. I think is great, very concise. Just follow along with it. You'll learn a ton in like a couple hours or less if you're new to all this stuff. Okay. Where were we? Overfit a small batch. So that being said, I'm not going to go into a ton of detail on how we actually, you know, why we zero the gradients, why we do the backward step, why we do optimizer.step. You should watch those tutorials. But this is all the standard stuff, right? We're making some predictions, getting a loss, right? Just using a mean squared error loss. And then we are basically just trying to get to the bottom of this function, right? We're just doing some gradient descent. I can't remember what optimizer I actually used, but we'll see. Oh, it's down below. So, all right, so let's look at this. Okay, so we're going to build our data module, make an instance of the data module, and then we are going to overfit. So we have 10 images, but training size 8, and I'm going to take the train data loader, so that's going to be 8 images that I'm going to overfit on, and oh, I actually don't think I need that. So let's do this. So this should not take very long, but I might pause it if it looks like it's going to take a second. Let's see real quick. Okay, so it's going pretty fast. I think it's going to be done shortly. So it's just blasting through these epochs, right? Okay, and it's done. So let's look at these predictions. So we're going to go model.eval. That's again something that you don't have to deal with when you're using pytorch-lightning. It deals with all of that for you for the most part. Let's make some, just see what the predictions are on our training data, right? So all we're doing is just predicting on the data that we just trained on. So there's nothing profound happening here. And what we're seeing is, oh, I called these logits. I don't know. These are really just like, but they're the raw outputs. It's not really probably correct to call them logits, but basically we see that the raw outputs are very close. All we're doing is rounding these and turning them into a long. And so, yeah, the predictions are spot on, right? These are the predictions. These are the labels or the targets, and those are spot on. Okay, so that's good. We've verified that we can overfit, and we can just visualize that overfitting as well here. So that was our data set, or half of it. Oh, I only overfit on 4 actually, because I only overfit on the first batch, which I made a batch size of 4. But it's just to demonstrate that things are working. Okay, so then if we display the labels and the predictions, we can see the background. So labels / targets are up in the upper left, and these are in the lower right. Oh, it's mirrored, but that's okay. So it's doing a great job, right? 1 rectangle, 1 line, 1 donut. It's guessing correctly for everything, as we saw. Okay, so thank you for staying with me here. We're going to actually train this model and hopefully learn something in the process. But the next step is to build the Lightning module, right? So this is the thing that, as I was saying before, is going to contain the model itself, the metrics. So it's going to track our metrics. It contains the loss function and the optimizer. So I'm not going to go into detail on every single one of these things, but this is really nice. And so you can also save an example input array. What that does is basically you can visualize the graph, so like the actual model itself, and it will pass this example array through it, and like you can get the shapes of everything. So it's basically like that track X shape that I put just for, you know, teaching purposes. It basically does that for you. Super nice. Okay, then we got our forward method. We just pass things, we normalize and then pass to the model. Again, normalizing the images, that's something that you could use these like torch transforms for, which is probably better practice, but I just didn't want to introduce too many things here, so I just, you know, it's easy. You just divide by 255, cast it as a float, divide by 255. Okay, then we have this custom histogram adder. This is cool. You can look at the histograms of your weights and biases over time to be sure that your model is actually learning something. And then we got our loss function and our training step. So the training step now, you don't need to put the like, you know, dot backward, dot step things like we're used to doing with vanilla PyTorch. All that is sort of, you know, is pushed under the rug into this abstraction of the torch-lightning module. So it's really nice, and yeah, please read the docs more about that, because this is really just going to illustrate how it works, but I'm not going into a ton of detail on each different step. Okay, so basically it takes the, oh, I don't know why this is, should not be there. It takes the images and labels and it passes them to the forward method. It gets the loss. It predicts, right? So I do a dot clamp just so we don't have negative predictions, and then it rounds those predictions and turns it to a long, and then it logs the metric. So I'm logging the accuracy and the F1 score of these predictions for both train and validation, and then it returns the loss. And so then basically like the stuff under the hood deals with like actually doing the optimization. Validation step is very similar. Okay, and then the optimizer I use, you need to put this configure optimizers method so that it knows what optimizer you're using, and I use Atom here. And then the learning rate, we make a parameter. And then this, just be careful that you put self.models.parameters, right, when you feed that to Atom, because if you just put model.parameters and you define model somewhere else, like it's going to be updating the wrong parameters, right? So, okay. Okay, so now we are going to go into the training, right? So this is what we've all been waiting for. Oh wait, let me get my microphone here. So unfortunately, I actually had to already run this cell. It took about 7 minutes or so to train, but it was messing with my film, my screen capture somehow. So I'll let you guys run this, but let's go through it. So first we build a data module. So we've got 7,000 images, 9:1 train val split. We've got 100 test images we can look at to see how it performed. Batch size of 16. We're going to shuffle the train, shuffle the validation. We're not going to shuffle the test because we aren't really doing, we're just visualizing some stuff with the test, you know, and I mean, like, technically we shouldn't even like look at the test until we build, you know, this sort of like the model that we're going to stand behind, but you know, we're just trying to learn stuff. So for now, that's fine. We just won't shuffle those, so we can just look at the same images with different models at different epochs and stuff. Okay. And then yeah, all this stuff is this classic stuff. So then we've got this checkpoint callback. This is basically what's going to do the saving of our weights and biases at each epoch, which is going to be nice because then we can look and see how the model has evolved over time. Okay, then we build our lightning module. So this, I don't like that this is all tabbed, but okay. So 3 in channels, those are the 3 shape dimensions, right? And then number of classes out is 2 because we did class probabilities 1, 1, 0, right? So since the last one is 0, there's not going to be any donuts. So there's just rectangles and lines for now. You can change this, try to get it to train on donuts too. Should work just as well. But I wanted to keep things simple here. And then we've got we define our model with this feature list, 8 and then 12 features, so it's pretty simple. And then yeah, we have the intermediate size for the fully connected layer of 10. Okay, then we have a logger here. That's really nice. This is going to be the TensorBoard logger where we can basically look and see in real time as we're training, like how the scalars and other things that we're logging over time are evolving. So these are going to be like our, training accuracy, training F1 score, validation accuracy, validation F1 score. But we're also going to log some other stuff that we'll look at. Then we got the device, and then we have an instance of a trainer here. So this is basically, this takes this information, the logger, the callbacks, the device, the number of epochs. I'm going to run for 50 epochs, and it is going to log every 5 steps, and then it is going to, so a step is like going through one batch, an epoch is going through one whole like walk through your data set, right? Then we call this trainer.fit. We give it the lightning module and the data module, and it trains. And it's really nice how simple that is, right? So then here we can look here, we can see, okay, it's using the CUDA, the GPU. It says it's missing a logging folder, but it just built that for me. And it's got my different parameters that I'm logging, my model. Okay, the model is almost 500,000 parameters, so that's actually kind of big, but not nearly as big as the millions of parameters in the Mask RCNN model. And then we've got an example of an in batch and an out batch, right? And it's going to be 16 by 2 because 2 for the number of objects in each class, right? And we're just going with 2 classes. Okay, so then we can look at this TensorBoard, which we load up here. I already have it loaded because this is I think it was the TensorBoard that was giving me trouble with filming my screen. And we can see the accuracy got, that's the training accuracy, so, whatever, but got really pretty close to 1. I mean, it didn't actually hit 1, which means maybe we're not overfitting. And the validation also looks reasonable. This is getting up to here. I'll scroll down so we have more of this in our screen. So here we're looking at the scalars, and we can see those over time, which is nice. And you can make any of these log scale or make them bigger. So yeah, then we can look at the graph. So this is really nice. So you can click in here and look at my object counter model and see the way that the images are passed through all the different layers and the different max pool layers through the linear layers. And if you zoom in here, you can see like the shape of things as they're being passed through these different layers. So super nice tool for debugging. yeah, I highly recommend logging the graphs to just get an intuition. And then we can look at the distributions. That was that little utility function. And we can see, okay, it looks like the distributions of our fully connected layer weights are changing a little bit, at least over time. Maybe the second layer is not. Maybe we don't need 2 layers, but yeah, they're evolving a little bit. So, and we can look through all of our different layers here, look at the weights and biases. So this, this feature extractor bias really evolved quite a lot. You can learn things, gain an intuition for which layers are kind of doing the heavy lifting. And then the histograms contain the same information, just displayed differently. And then the hyperparameters. So I should show you how this saves it. So if we go over here to the tension board logs and to our experiment, then it's going to have a version 0. So if you run that cell above again, it'll make a version 1 and so on, right? So you can have all these different versions saved here and compare them head to head, and then look at which features, or I'm sorry, hyperparameters, gave you the best performance. And then in here we have all of our checkpoints, which contain the weights for each of the 50 epochs that we ran. Okay, so that's that. And then, okay, so yeah, let's look at some test data here. I already looked, but we'll look at some. So this is now just, we're looking at data. We're going to predict on data that the model has never seen, right? What training or val. And let's see how it does. Okay, so I'm only displaying the predictions. You could display the labels as well here, but we can kind of just tell what is in these images, right? So I'm not going to do that for now. And so, okay, this first one, it's saying this is background. That's great. This second one, it's saying 2 rectangles. Okay, nice. That's right. 2 rectangles again. That's right. Background, background. Here it's saying 1 rectangle, 1 line. Okay, so that was incorrect. But it's kind of understandable. They're overlapping. Here, 2 rectangles, 1 rectangle, 1 line. 2 rectangles, 1 line. 2 lines, 1 rectangle. Correct, 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 correct. I was even able to differentiate those 2, background and correct. Okay, so it's it's performing pretty well. I mean, we could look through some more and see, but it's doing a pretty good job. I mean, it's not perfect because the accuracy was only like 94%, but this is working to first order. And yeah, people should go mess around, add the donuts, make an imbalanced data set. I have sort of a list down below on like what I think would be useful to mess around with. But okay, that is all for that. And then here I have a way that we can visualize the first conv layer. So what we've done here is we're loading the path. Well, we take the path to this checkpoint here, and then we load from checkpoint. So this is really nice. You just have to do lightning object counter. So that's our lightning module dot load from checkpoint, right? And now it's loaded up with those weights and biases. So that's really nice. And then we can extract some of the weights from this conv layer and visualize those. And then so here I just normalize the list of kernels and visualize them. So remember, let's go up here because this is going to be interesting. So the up a little further, sorry. So the feature list that we fed it was where? Here, 8, 12, right? So the first conv layer was going to extract those 8 features, right? So let's understand what's going on here. So the shape of this first conv layer weights is 8, 3, 3, 3, right? Because, why? Because there are 3 3 color dimensions, and it wants to extract 8 features, right? So it applies that to the 3 color dimensions, and it gets 8 out, right? When it convolves with the image. And then the last 2 set of 3s here, those are for, because we set the kernel size equal to 3, right? That's the filter size basically, right? So we basically have 8 3x3 filters, and each of them has 3 color dimensions. So I hope that's not confusing to people, but think about the shapes there, and how you can extract the 8 features by applying these 8 filters. Okay, so then we can now scroll through these weights and see that they are indeed changing. So the model has been learning something about which of these different filters are most, valuable for the predictive power of the model, right? Because remember, the weights of these filters are what actually get convolved with the image, right? So that could be like one of them could extract edges or something, right? Like maybe one of them detects edges and then another of them detects like, a bend or something like this, right? Okay, so wrapping up here, let's go on to the conclusion. So thank you for staying with me here. I just have a little bit more, and I hope this has been useful. So we built a from scratch implementation of an object counting model. We trained the model on a simple and flexible data set that we built from scratch using NumPy, and gained some intuition for how images actually work. And like images in the end are just tensors or just arrays at the end of the day. So then we got started getting the hang of pytorch-lightning, and we visualized a conv 2D layer here at the end. And I hope also there were some useful tools there for you when you're using pytorch-lightning on your own to save things and save weights and biases for the different epochs, and visualizing the histograms and the distributions and visualizing the graph. Those are all great ways to debug as you go when you're building a new model. Okay, so how to use these classes and functions in your own project. This is the final thing, but stay around for it because this is going to be useful. So all of the functions up top that we went through, all the classes and all the methods are, well, I should say classes and the sort of utility functions are built into this PyTorch tutorials package that I built. And so we can click through here. We're gonna install this. So these cells from here down, you can just copy and paste these into your own notebook and start making a little sandbox for yourself to mess around with these things very easily. So all of those are in these this package here, and there's basically just 4 modules. CV stands for computer vision, so there's utility, data sets, models, and data modules. So let's look through this. So the version, oh, it didn't like that. Did I not run this? Okay, I didn't run that cell. Okay, so 2.14, 0.2.14 is the version, a resource for learning about PyTorch and deep learning. I should probably make that description a little more informative. And then this is the link to the GitHub page for the project. Okay, so here we're just going to real quick, not go through much in detail, but just to show how you can use any of those above methods with by using this package. So here we can grab the data module, object counting data module, and then we can visualize it with the utility function add labels, right? So CV utility, we just imported that from the PyTorch tutorials library, and we've now used the show utility function, and we're visualizing these and we're yeah, we're doing it. So now I don't know why I have this twice. We can also get the model, so that double conv model is there if you want to use that to build up other models. You know, and then also this object counter model is in the package as well. So you can, you know, use any of these just as we use them here. The lightning module itself, I did not build into the package because I just think that is something that is probably best just made by the specific researcher or user at the time of the application. So, but everything else is built in there, and you can obviously just steal my code for the lightning module. Okay, so that is it, and I hope that was useful to people. Thank you very much. Bye.